So, starting with the last term question, it says explain why the graph is flat between points A and B. So, we know that when you heat a substance up, two things can happen. One, that energy can be used to raise the temperature of that substance so it gets hotter. Or, alternatively, the energy can be taken in to break the existing bonds or forces between particles, which causes that change of state. In this case, the graph is flat because the energy has been taken in to break bonds instead of making it hotter. So when it's changing state, so it's melting from solid into liquid, the graph is flat because it's no longer getting hotter, but the energy is being taken in to break existing interactions instead. You've then been asked to give the electron configuration of the following atoms. So sodium, if you look at the periodic table, has 11 electrons. We know that 2 can fit in the first shell, 8 can sit in the second shell, and that leaves 1 left over for the third shell. Chlorine has 17 electrons, so that means 2 can fit in the first shell, 8 can fit in the second shell, and 7 can fit in the outer shell. Magnesium has 12 electrons, so 2 can fit in the first shell, 8 in the second shell, and 2 in the final shell. And as you'll check in the exam, we know sodium's group 1, there's 1 electron in the outer shell. Chlorine's group 7, there are 7 electrons in the outer shell. And magnesium's group 2, there are 2 electrons in the outer shell. You've then been asked to explain the melting point of sodium chloride. So the first thing you need to do is decide whether it is ionic or covalent. So sodium is a metal because it's on the left-hand side of the periodic table. Chlorine's a non-metal because it's on the right-hand side of the periodic table. And we know bonding between a metal and a non-metal is ionic. So it's basically saying, explain the melting point of ionic compounds. We know it's high because it's a strong electrostatic force of attraction between the oppositely charged ions, the positive sodium and the negative chloride ion. You've then been asked a similar question, but for hydrogen chloride. So again, we need to think about what type of bonding is present in hydrogen chloride. We know hydrogen is a non-metal, chlorine is a non-metal, and that means the bonding must be covalent because it's between 2 non-metals. So you are asked to explain the melting point of covalent compounds. We haven't looked at giant covalent yet, so we'll assume and we know it's simple molecular or simple covalent. So we know the melting point is low because there are weak intermolecular forces between molecules, so little energy is needed to overcome them. So this lesson, we're going to move on towards looking at our giant covalent structures, and in particular, we're going to look at 3 specific examples, which are our allotropes of carbon. So if we just do a quick recap in terms of understanding the basics to make sure we can access this lesson. A covalent bond is our shared pair of electrons. So one covalent bond involves 2 electrons being shared, one from one of the atoms in the bond, the other comes from the other atom in the bond, and we use a dot and cross to represent where those electrons have came from. We also said last lesson that covalently bonded substances can form 2 structures, simple molecular and giant covalent. So this lesson we're going to focus on giant covalent substances, and we've got to look at specific examples in turn. So a giant covalent substance has the structure like you can see on the left. So it contains lots of atoms, and these lines between each atom are our strong covalent bonds. So as you can see from the diagram, it's got many strong covalent bonds. Here, there are no intermolecular forces. So last lesson, we said we never break covalent bonds for simple molecular because the covalent bonds are too strong, and instead we only need to overcome the weak intermolecular forces. In this example, there are no intermolecular forces, so the only thing we can do in order to melt or boil this substance will be to break all of these bonds, shown by the lines, between each of the atoms. So therefore, we've got to break the many strong covalent bonds, so that means the melting and boiling point is going to be high. And your perfect textbook answer will be that there are many strong covalent bonds, so a lot of energy is needed to overcome them. If we think back to conductivity, we said we need charge and we need movement. In this case, we don't have ions because it's covalent. We do have electrons, but they're all fixed inside our covalent bonds, so we have no free electrons or ions. There is one exception, and we'll look at that in turn, but generally, giant covalent compounds or substances do not conduct electricity because there are no free electrons or ions. So our exception that we'll look on later on is graphite. Moving on to our more specific examples, an allotrope is a different version of the same element. So if we've got the same element and you structure it differently, you can result in different substances being formed. So let's take carbon as our base element. If we take carbon and we rearrange its structure, you might end up with graphite, which is used in pencils, graphene, which is used in pacemakers for hearts, or diamond, which is used in jewellery. All of those three substances only contain carbon, but in each of them, the carbon is arranged in a different way, which gives rise to unique properties and therefore determines the way we can use it. So, using either the info sheet or your own research or the CGP revision guides, try and answer the questions on the next couple of slides. So pause the video, have a go, and then we'll go through the answers so you know what you need to write for each one. So we know diamond, graphite, graphene and Buckminster fullerenes are all allotropes of carbon, and an allotrope is a different physical form of the same element. If we look at diamond, this is the structure of diamond on the left. So you can see we've got this giant network of atoms all held together by strong covalent bonds. And if you look at the diagram, there are many strong covalent bonds. So this is going to be a giant covalent substance. Carbon is in group 4. That means it can form 4 covalent bonds because that's how many it needs to get a full outer shell. If it's giant covalent, the melting and boiling point will be high, extremely high, because lots of energy is needed to break the many strong covalent bonds. It can't conduct, and the reason for that is there are no free electrons or ions to move and carry that charge. Now, in terms of uses of diamond, there are 2 that you could use. You could say jewellery, and the reason it's used as jewellery is because it's got this really rigid and hard structure. Okay, so it's obviously it won't dissolve, it won't break down. Alternatively, it's used in cutting tools, so it's actually used in drills to cut other substances, and again, it links back to its really rigid and hard structure. If we move on to graphite, what we use in pencils, graphite has the structure that you can see on the left. So we've got these rings of carbon atoms, all covalently bonded, and you can see there are lots and lots of many strong covalent bonds. So graphite is also giant covalent. However, the difference between graphite and diamond is instead of forming 4 covalent bonds, each carbon atom only forms 3. So they can form 4, but in graphite they only form 3. That results in this different structure to diamond. It's got a high melting point because lots of energy is needed to overcome the strong covalent bonds because it is giant covalent. And if you think back to our earlier slide, we said graphite was the only example of a giant covalent compound that can conduct electricity. And the reason for that is if each carbon only makes 3 covalent bonds, that means every carbon atom in graphite, so every circle you see here is a carbon atom, each of them has 1 delocalized electron. That delocalized electron can move between the layers and carry the charge, so that when an electrical current is applied, the electron moves between the layers, carries the charge, so electricity flows from here all the way throughout the structure. The word delocalized we haven't really looked at yet basically means it's not fixed, so it's not local to one position, so it can move. So we say electrons are delocalized in graphite and also in metallic bonding as well. A use of graphite, so there should be graphite, is it's used in pencils, and that's because it's soft and slippery, and that's because these layers can slide over each other. And it's also used as lubricant, so like oils, and again it's soft and slippery. because the layers can slide over each other. Buckminster fullerenes are allotropes of carbon arranged in these kinds of rings or balls. So they are our Buckminster fullerenes. Now, there are lots of covalent bonds, but they're actually really, really small. There's about 60. So even though we do have many covalent bonds, it's simple molecular because these structures are actually extremely small. Each carbon atom forms 3 covalent bonds. The melting and boiling point is low, and that's because if it's simple molecular, we know the rule is we don't break covalent bonds for simple molecular, only for giant. In simple molecular, what we break is those weak intermolecular forces of attraction between molecules, or in this case, the different spheres. It can't conduct electricity because even though there's a delocalized electron, it can't move between the spheres. So that electrical current can't move from sphere to sphere, so it doesn't conduct overall. The last allotrope you need to know in detail is graphene. Now, graphene is essentially the same as graphite, but it's 1 layer thick. So if we think about graphite, it has our 3 layers of carbon in hexagonal rings. This is just 1 layer thin. And I believe the researchers who developed this and found its applications recently won the Nobel Prize from the University of Manchester for discovering graphene and making it essentially 1 atom thick. So it is giant covalent because it's very similar to graphite. Like graphite, each carbon forms 3 covalent bonds. It's got a high melting point because the many strong covalent bonds require lots of energy to break. It will conduct electricity because this time the delocalized electron for each carbon atom can move right throughout the structure to allow an electrical current to flow. And the link between graphite and graphene is the same, it's just 1 layer. So this slide is just showing you some of the practical applications of these structures and the researchers who developed these structures. So it says researchers have developed the first cardiac implant made from graphene. It works like a normal pacemaker, so it senses irregularities in the heartbeat and it delivers an electrical impulse to essentially make sure the heart beats on a more regular rhythm. So it makes it beat more normally. So you can see this graphene tattoo. It's the thinnest pacemaker ever created. And obviously the structure of graphene makes it extremely suitable for this purpose. So pause the slide and have a go at answering these 3 questions just to check your understanding of giant covalent compounds. So question 1 says, give 2 reasons why graphene is suitable for making a cardiac implant. Well, graphene is 1 layer thin, so it's extremely thin, which allows it obviously to be moulded to the heart, to the muscle tissue, and it's also a conductor of electricity because we've got delocalized electrons which can move throughout the structure. The structure of graphene is that it's 1 layer of graphite, so it's giant covalent, so there are many strong covalent bonds, which means there's a high melting point, high boiling point because we need lots of energy to break those, but it will conduct electricity because each carbon atom has a free delocalized electron which moves throughout the structure to carry an electrical charge.